This is the parent graphs for section 2.4 notes. Today we're going to go through what the parent graphs for 7 kind of standard graphs look like that we're going to be exploring in the next 2 chapters. So the first graph that we're going to be looking at is our even-powered power function, f of x equals x squared. The shape of this graph is going to be a parabola. Hopefully you remember that. And our standard, just f of x equals x squared, has a vertex here at 0, 0. And remember that that axis of symmetry runs down the middle of the graph and is like a mirror in the center of the graph. So if we were to plug in -1, we would get +1. If we were to plug in +1, we'd get +1. If we plug in -2, we get +4. And if we plug in +2, we get +4. So if I quickly graph these points, my parabola is going to look like this. And that's what we would call the parent graph of x squared. Now, of course, we can have a shifted graph where we start talking about our transformations, and this is going to look like f of x equals a times x minus h squared plus k. And that h and k are going to keep popping up, so maybe up here at the top we should write that h is our horizontal shift, left and right, and k is our vertical shift, up and down. And that's the same for all of these transformations. Our second graph is an odd power function, so for example, an x cubed. And the shape of this graph, I call it a standing snake. And again, if we just kind of choose our fave 5 here for x values, -2, -1, 0, 1, and +2, and we plug these in, we're going to get -8, -1, 0, 1, and 8. And so, of course, my graph doesn't accommodate all these points, but I'll do my best here. So 0, 0, 1, 1, and -1, -1, and then 2. 8's going to be like up here. And -2, -8 is going to be about down there. And so this is what my parent graph looks like for f of x equals x cubed. And again, our shifted version, if we had shifts, would be f of x equals a times the quantity x minus h cubed plus k. The next graph we're going to look at is the root function, and this is what a root function looks like with an even index. It is going to be a sideways half parabola. That's kind of what a root graph looks like. And it doesn't make any sense for us to choose any negative x values here, because if we have an even root, then the smallest x value that we could possibly have under our root would be 0. So I'm going to choose 0, 1, 4, and 9. I chose those x values specifically because they're perfect squares, so when I take the square root of them, I'm going to get nice numbers here. And the square roots of all those numbers are 1, 2, and 3. So when I plot these points, I've got 0, 0, I've got 1, 1, I've got 4, 2, and then 9, 3 would be off my graph. So you can kind of see that's my sideways half parabola there. And again, my shifted version, once we get to our transformations, is going to be f of x equals a times the square root of x minus h, and h is under the radical, and then plus k, where k is after the radical. We can also have root functions with an odd index, and I call these the sleeping snakes. Power functions are standing snakes, and root functions are sleeping snakes. Now, when our root is odd, we are allowed to have negative numbers underneath the radical. So for this one, I'm going to be very specific about my x values, because if my root is 3, if I'm graphing a cube root, then I'm going to choose only perfect cubes so that I have some nice values to graph here. So I am going to choose -8, -1, 0, 1, and +8. These are kind of the standard set of x values for the cube root of x function. So then the cube root of negative 8 is negative 2, cube root of negative 1 is negative 1, cube root of 0 is 0, cube root of 1 is 1, and cube root of 8 is 2. So I will graph what I'm able to graph here. And these are kind of off my graph, but it's going to look something like that. And the shifted version of this would be f of x equals a times the cube root of x minus h under the radical and plus k after the radical. Okay, these are probably going to be new. Okay, our reciprocal functions, we can have either odd powers or even powers with these. If you have an odd power, meaning we have 1 over x to the first power, these are going to contain asymptotes. We're going to have a vertical asymptote at x equals 0, and we're going to have a horizontal asymptote at y equals 0. And as the semester goes on, we will be learning more about why we have those particular asymptotes. But for right now, we're just going to, I'm going to graph those asymptotes here with some yellow lines. And remember, an asymptote is a line that a graph approaches but never crosses. Okay, so now if we go back to our shape of our graph, it's kind of, I don't know exactly how to describe this, so I'm just going to say that it has 2 branches, and of those 2 branches, one is going to be up and one is going to be down. And you'll see what I mean in a second when we graph this, because the even-powered reciprocal functions have 2 branches, but they're both up. Okay, so that'll kind of be the difference between these two. I am going to expand my table quite a bit more so that you can see the shape of what's going on. But once you understand the shape of this graph, then you should be able to kind of just translate the graph to a different location in the coordinate plane based on what your shifts are going to be. So I'm going to do, for my x values, negative 2, negative 1, negative 1/2, 0, positive 1/2, positive 1, and positive 2. Sorry, I guess I added more than I needed to down there. All right, so when I start plugging these in, remember that I'm thinking about reciprocals here. So 1 over negative 2, that gives me negative 1/2. When I plug in negative 1, 1 divided by negative 1 is negative 1. When I plug in negative 1/2, 1 divided by negative 1/2 is like 1 times negative 2. So that's going to give me negative 2. When I plug in 0, my graph is undefined because we can't divide by 0. That's why we have a vertical asymptote there. When I plug in 1/2, 1 divided by 1/2 is positive 2. When I plug in 1, 1 divided by 1 is 1. And when I plug in 2, 1 divided by 2 is 1/2. So now I'm going to go ahead and I'm going to plot these points. When x is negative 2, y is negative 1/2. When x is negative 1, we're at negative 1. When x is at negative 1/2, we are at negative 2. So this is our kind of down branch or our lower branch here. And then we have that undefined zone in the middle there where our asymptotes intersect. And then when x is positive 1/2, y is 2. When x is 1, y is 1. And when x is positive 2, y is positive 1/2. So this is our upper branch, or it's above our x-axis. So that is what a reciprocal function with an odd power is going to look like. When we have an even power, we have the same 2 asymptotes. So we're going to have a vertical asymptote again at x equals 0, and we're going to have a horizontal asymptote again at y equals 0. So I'm going to go ahead and I'm going to sketch in those asymptotes again, just like I did on the previous graph here. Kind of highlighted lines. And then the shape of my graph this time is still going to be 2 branches. But this time my 2 branches are going to be both up. Okay, so I'm going to go ahead and I'm going to add 3 more boxes here in my table. And I'm going to choose the exact same x values as I did before. Negative 2, negative 1, negative 1/2, 0, positive 1/2, positive 1, and positive 2. And when I plug those in, now remember this time I'm squaring them. So 1 over negative 2 squared is going to give me 1/4. 1 divided by negative 1 squared gives me a positive 1. And 1 divided by negative 1/2 squared is going to give me a positive 4. When I plug in 0, remember that will be undefined still. 1 over 1/2 squared is going to give me 4 again. 1 over 1 squared is going to give me 1. And 1 over 2 squared is going to give me 1/4. So now I'm going to go ahead and plot these points. When x is negative 2, y is 1/4. When x is negative 1, y is 1. When x is negative 1/2, y is 4. So this branch right here on the left side of my y-axis looks like that. And then I'm going to have a mirror image of it on the other side of my x-axis. When x is positive 1/2, we have 4. When x is positive 1, we have 1. And when x is positive 2, we have 1/4. So that's what our reciprocal functions look like. Now, of course, with both of these, we can have shifted versions. So the shifted version of our odd-powered reciprocal function is going to look like f of x equals 1 over x minus h in the denominator plus k. And the shifted version of our even-powered reciprocal function is going to look like 1 over x minus h quantity squared plus k. The last parent graph that we're going to talk about should be familiar to you. I know we cover this in Algebra 2. This is our absolute value function. And these functions, they're very easy to distinguish because they are always V-shaped. And the slope of the left side is always opposite, but the same slope but opposite as the slope of the right side of the graph. So the easiest table to make here is just our fave 5, negative 2, negative 1, 0, 1, and we'll throw on an x equals 2 here. And when we plug these in, absolute value is always positive. So the absolute value of negative 2 is 2, absolute value of negative 1 is 1, 0 is 0, absolute value of 1 is 1, and of 2 is 2. So we have that vertex there at 0, 0 for our V shape. And then when x is negative 2, y is positive 2. When x is negative 1, y is positive 1. And then on the other side, we have the reflections of those points. And so this is our absolute value graph, our parent graph here. And of course, just like the others, we can have a shifted version of this graph. And our shifted version is going to look like f of x equals a times the absolute value of the quantity x minus h inside the bars plus k outside the absolute value bars. So these are the parent graphs that you should study and know so that when you have to graph them and you have to graph transformations of them, you don't necessarily have to build a table each time. You know what they look like, you know where they normally would begin or end and what the shape of them would be, and then you can just apply the transformations so that you can graph just the transformed graph based on your shifts, your stretches, and your shrinks, which we will be talking more about in the next few days.